Hi all, this is Mr. Yeager for Chem, and this is kind of the second part of the electron configuration video, where we just finished in the prior video how to write out electron configurations, but now there are two other ways to illustrate how the organization of the electrons. And that's what we're going to go over with orbital notation and then noble gas notation. So with orbital notation, okay, electron configuration, that method I showed last video is kind of the foundation for the rest of this. Okay, so you need to be able to write out that electron configuration to then be able to do this orbital notation. And then the noble gas is actually going to be an abbreviated method. So with the orbital notation, this is where we are more specifically drawing out the arrangement of the electrons in that electron configuration. Okay? And so what we use here is arrows represent electrons and orbitals are represented by boxes or a line. Okay, you can see obviously there's boxes in the pictures over there, but you can also just write like 1s with a line, 2s with a line, etc. Okay, now with this we do have to understand the number of orbitals based on the sublevel. Okay. So we already said like S has 6 electrons, or that's wrong, 2 electrons in it, okay? The S subshell can only hold maximum of 2 electrons, and that's because there's only one orbital, one box, one line in the S subshell, okay? And you can kind of see that up here. 1s, there's one box. 2s, there's one box. When you get to P, there's actually 3 orbitals. And it's because each orbital can hold up to 2 electrons, 2 arrows. So you can get 6 electrons in the P subshell, but they'll be separated out in different orbitals. All right? And one of the rules is when we have multiple orbitals on the same subshell, you have to add 1 electron in each of them first before you start going back and adding a second electron. And that goes with the idea that electrons are negative. They don't want to be close together unless they have to be, and it helps them with the energy. So right here, since they're all at the same energy, let's spread them out until we have to pair them up. Okay? When we get to D, we're going to see D has 10 electrons again, which means there's 5 orbitals. Again, we basically just divide the maximum number of electrons by 2, and that's how many boxes we have. We do include the orbitals even if they're empty. So if you drew 2p and you only drew 1 line, that would be marked wrong. You need to draw 3 lines or 3 boxes with 2p, and even if there's only 2 electrons, you need to leave the other one blank. It needs to sit there, and I need to see it. All right? So that's what you're looking at with these. Now the last thing you can notice right here is that when you place the electrons together in the same box, the arrows have to be opposite. So one has to be pointing up and one has to be pointing down. There are specific names to all these rules. We're not covering those. If you want to look them up, we're now doing what's called the Hund's rule, and we're doing the Pauli exclusion principle, and we're not really covering that in much detail here. Okay? So if I do an example here, I have sodium. Okay? So sodium has 11 electrons. So my suggestion would be that you write out the electron configuration for this. So, I mean, I'm not going to bring back up the Alkwall diagram, but this would be 1s2, 2s2, 2p6, 3s1. And the reason I do that is now you can put in here the correct number of orbital lines. So S's always only have 1 line or 1 box. Okay? So all the S's are only going to be 1 box. But P is 3, so we got to put 3 here. So however you want to do that, 1, 2, 3. There has to be 3 boxes. And then what we do is we just fill it up. If you have the maximum number, you have 1 up arrow, 1 down arrow, 1 up arrow, 1 down arrow. Right here, technically this is filled up, 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 and then down, 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 because we have 6. Then when we get to the very end, this is kind of the one, even though I'm looking at everything, like everything should be filled up to the end. This is where I'm looking that you only put 1 in there, because it's 3s1. So it's that 1 extra electron at the end there. So again, I got my configuration. I know the off-ball diagram in my head. So, but that would be, you have that in front of you, and you can kind of go through it piece by piece, going 1s2, 2s2, 2p6, 3s1, and then drawing in the arrows. Boron. This will be a short one. Boron only has 5 electrons. So the electron configuration would be 1s2, 2s2, 2p1. Again, following the off-ball diagram. S only has 1 box or 1 line. S, only 1 box, 1 line. P, 3 boxes. 3 orbitals. The first 2 are going to be all filled up. The last one, I only have one electron. So, I mean, the common thing is just to put it in the far left box. Fill it up from the left to the right. Another one. I don't think we're going to do all of these, but there's more out there. Let's look at krypton. Krypton. Ooh, this has 36 electrons. There's going to be a lot of arrows. So with krypton, this is a good one. This will probably be the last one. This would be 1s2, 2s2, 2p6. I hope you're following along with your off-ball diagram if you're watching me do this. 3s2, 3p6, 4s2. I got to keep going. 3d10, and then 4p6. If I add this all up, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6, that would be 36. All right, all of the S's, they have only 1 box. So all the S's, just 1 box, 1 box, 1 box, 1 box. The P's, they'll have 3 boxes, 3 orbitals. D, we haven't done D yet, but that would be 5. Again, you can only get 2 in each one, so that 10 divided by 2 is 5. And then we got to fill them all up. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. I'll do this one correctly, technically. Up, 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 down, down, down. 1, 2. This technically would be up, 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 down, 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 down. And then we got 6. This is the one we got to check because we might not fill it all up, but it's 6, so we will be filling it up. 1, 2, 3, 4, 5, 6. And that is krypton. All right. 3 examples is more than enough. I mean, you could continue going through some other ones if you want. You could try these other ones: magnesium, titanium, chlorine. If you're my student, obviously you can come in and show me, but we'll be practicing as well. Okay? So that's the idea there. Last type of notation. All right, this is the one that everybody's like, oh, why can't I just do this all the time? This is the noble gas notation. Okay, and as I already said, and it says there, it's the abbreviated version of the electron configuration. So this one, you get to kind of make life a little bit easier. What you do is you find the element that it gives you, and the initial part of the configuration is replaced by the noble gas. So in other words, you find your element on the periodic table, you go to the row above it, the period above it, and you write the noble gas on that period that is above the row that your element is on. So I'm going to pull up my periodic table again so we can see this a little bit easier. But by writing that noble gas, as you can see over on the side here, writing the noble gas in brackets represents the entire electron configuration up to that noble gas. And then all you have to do is complete the rest of the electron configuration from that point forward, okay, for that last row. So you don't have a lot to do with it, all right? So like, I mean, the helium, the beginning ones, it doesn't really matter. Like helium is only saying 1s2, but neon, by writing brackets neon, that's technically saying 1s2, 2s2, 2p6. So it's taking care of the first 2 rows of the electron configuration, looking at it from a periodic table perspective. Okay? With the off-ball diagram, you're going to have to be careful because you're going to have to be like, neon is 2p6, so be done that part of the off-ball diagram and get to the next one after 2p6, which would be 3s1. So I'll try to use the off-ball diagram first. Let's see what examples they're giving us here. Fluorine, rubidium, oxygen, iron. Okay. So let's go back. Let's try to use your diagram, your off-ball diagram. So one of the first ones I saw was rubidium, Rb. Okay, so we find Rb, it is number 37 on the periodic table. And so what I would do is I would look at Rb. Let's actually leave this for a second. Sorry, let me come back, because I do need it. We should look at a periodic table with this. So I'm looking at Rb, okay? And what I do is I go up one row all the way over to the noble gases, again being the last column. And what you're going to write is you're going to write krypton in brackets. What you have just done is you have now taken care of the electron configuration for the first 36 of the 37 electrons in rubidium. So instead of writing 1s2, 2s2, 2p6, 3s2, etc., you're just writing krypton, and you've now already gotten to, this would be 4p6. All right, and that's another thing we're going to have to play around with on the electron configuration, is the electron configuration, you should be able to identify the last part of it and identify the element based on the last part of the electron configuration. Okay, so 4p6 is krypton. So if I go back, and I use my off-ball diagram to help me with this, if I'm doing rubidium, 37 electrons, and I've just figured out that I'm doing krypton as the noble gas on the row above it. Krypton gets you here. So you've taken care of all of these down here and this one. Because again, you've already gone through that arrow. We just finished 4p. What's after 4p? It's 5s, and that would just be 5s1. All right, because krypton is 36 electrons shown. I just need to show that last one. That's 5s1. Okay? All right. Let's look at another one. So I think the next one was, I'm going to just say oxygen. I'm going to have to kind of go back and forth a little bit. So oxygen is going to be clearly a bit shorter. With oxygen, you're all the way up here. You go to the row above and over to the noble gases. So we would start oxygen with He brackets, which really just represents 1s2. But if I'm doing noble gas configuration, I need to write He. I would then continue on from that point forward. So the configuration, I'm not going to go ahead and put it into full mode there. So with He, sorry, we're doing oxygen, which only has 8 electrons. You've already taken care of this, so you're just immediately going to the next one. He only takes care of that. It finishes up that arrow. So we would do 2s2, and then I'm going to 2p, and it's going to be 2p4. Because again, this is technically 1s2, so that's already 2 electrons, 4, 8. Okay? Let's do one more. We'll pick one more out there. I'll just pick a random element. Let's say that I want to do, let's go ahead and do cobalt. So if I do cobalt and I say write the noble gas configuration, I go up one row all the way to the end. So this is going to be argon. Okay? Argon, if we got to this point, will be 3p6. Okay? So you've taken care of everything from 1s2 all the way to 3p6. And I just need to get up to 27. So this is already 18 electrons done, and I need to try to get to 27 electrons. All right, so I write argon, and that has already gotten me through 3p. So I keep going, and again, that's 18 electrons, and I'm trying to get to, let's say, 27. Okay, so my next thing would be 4s2, so that's 20, and then I'm hitting D, and D can hold up to 10, but I already have 20 electrons done, so there's only 7 left, so that would be 3d7. And again, the noble gas configuration is just a shorter method than writing out everything to get to that point. It's just a shorter, abbreviated method for you to use. It's just going to take some practice to go through it. All right, that's it. Thank you.